So today we're going to see in detail something that you've already seen. So what quantum physics does, it's nice because you might have already seen certain things. It lets you see the same things in a different light, in a deeper light. That's the power of quantum physics. These are not new concepts. Many concepts are new, but old concepts, traditional concepts, can also take up a new form. And the one thing that we're going to discuss today is something that you've been seeing since your O levels. That's the hydrogen atom. Now, hydrogen, as you know, is the most abundant element in the universe. 99% of the universe is hydrogen. And more than half of what's left is helium. And then you have the 120 or 30 other elements taking a small sector in the big pie. So today we want to see what the hydrogen atom looks like from the point of view of wave functions. So I hope you've seen the hydrogen atom's orbitals in your Chem 101 lecture already. So let's start off by looking at the wave functions inside a hydrogen atom, and we'll look at the wave functions of an electron. We're not focusing on the proton inside the hydrogen atom, rather we're looking at the electron inside the hydrogen atom. So first of all, I would like to ask for a volunteer who could write down the Schrodinger equation for me in 1D. Come on. Anyone? Any takers? Ajay? Schrodinger equation, आप लिख दो. I know you know everything.
नहीं सर.
चलो कोशिश करो. इधर. अच्छी सी. Time independent.
सर वो तो नहीं आती.
So let me give you a hint. So chalk पकड़ लो एक और. So on the right hand side you have the wave function being multiplied with the energy.
सर इतना मुझे याद है.
So all right.
Multiplied by the wave function.
Right. The wave function आगे चलो.
इधर नहीं था. Plus.
All right.
इतना मुझे याद.
So the energy must have a potential energy part and a kinetic energy part. So the potential energy part is V. V itself can be a function of position. We've seen many examples of this. And we need something extra here. What is that extra? So right. So we need kinetic energy. Kinetic energy in quantum physics comes as an operator, as a differential operator. So it's kind of the double derivative of something. Yes? And there is some constants with this, which is minus h bar square over 2m.
ठीक है सर.
Alright. So I think the eat break has taken a toll on many of you, but alright. So this is the time independent Schrodinger equation. Since I like my blackboards to be neat, so let me rewrite this. So I have minus h bar square over 2m So this is the Schrodinger equation in 1D. You solve this equation, you get the wave functions, and then you can put in a time dependent part later on. And you will see that the energy is quantized if you have a bound system, and we've seen several examples of this. So this is in 1 dimensions. We've already seen 3-dimensional quantum wave functions. For example, we studied a 3-dimensional infinite web. So how does this scenario change in 3D? So now you have 3 variables, x, y, and z. So the wave function is now dependent upon x, y, and z. And your energy, now the potential energy can also depend upon x, y, and z. Wave function x, y, z plus minus h bar square 2m. Now what about this second order derivatives, you have three kinds of them. So I have an x part, a y part, and a z part, and all three of them act on the wave function. Right? So this is the three-dimensional Schrodinger equation, and we solve this for an infinite well. By the way, in one of your quizzes, the next quiz, I'm going to ask about a two-dimensional or three-dimensional problem. All right, so you better brush up your infinite wells and the 2D and 3D configurations as well. So this is in 3D. But let's look at the hydrogen atom. In the hydrogen atom, we have an electron around a nucleus. And what is the nucleus in the hydrogen atom? It's just a proton. That's it. It doesn't have a neutron. So the hydrogen isotope is the most abundant isotope is just a proton. So for an electron that is seeing a nucleus, what kind of forces is it seeing? What kind of fields does it see? What kind of interaction does it have with the proton?
Electrostatic.
It's electrostatic. So if you have a point charge, so some charge q on the proton, what kind of electric fields does it produce? It's radial. All right, so if I were to draw a sphere around this proton, sphere is at a fixed distance and the proton is at the center of this sphere. On all the points of the sphere, the electric field is going to be equal. It might be pointing in different directions, the radial direction, but it's going to be the uniform on the sphere. So no matter where the electron is on the sphere, whose center is the nucleus, is going to experience the same field, the same force. All right. So such a kind of potential is called a spherically symmetrical potential. It's symmetric spherically. Got it? Now for problems of this kind, you don't want to use the coordinates x, y, and z. Even in this case, you do encounter, you have an x-axis, you have a y-axis, and you have a z-axis. But if you move on the sphere, x, y, z change. But it becomes very cumbersome to keep track of these variables. When you have a situation that is spherically symmetric, it's customary to use another set of variables, which are called the polar variables or the spherical variables. So in this case, you have a point on the sphere, and this point on the sphere is characterized by three quantities. It has an r, it has a theta, and it has a phi. So if I were to draw let me draw a better diagram over here, a bigger diagram. Let me draw a sphere, big sphere. I take a point P, some point on this sphere. First of all, I draw axes, an x-axis, a y-axis, and a z-axis. This point on the sphere P, it's identified by three variables. One of them is simply the distance from the origin. That's r radius. The other thing is, now if I connect this point with the equatorial plane, I get an arc. So how, there are two more variables that I need to specify. One is the angle theta, which signifies how below the north pole am I. So if I'm on the vertical axis, theta is 0. If I'm on the equatorial plane, theta is 90 degrees. So this angle, theta, is the angle of cold attitude. We've already seen this for the Bloch spheres. The third point is that if I were to follow this arc and land on the equatorial plane, I could also draw another angle which specifies my inclination from the x-axis, phi. I have three variables now, r, theta and phi. We've already seen this for the Bloch sphere, but right now I'm not talking about the Bloch sphere. This is not the Bloch sphere. This is a point on a sphere in real space. It's not quantum space, it's real space. So I need, in order to identify the position, I can specify three kinds of variables, r, theta and phi. These are called my polar coordinates or my spherical coordinates. R, theta and phi can be equally used. In fact, they provide more convenience as compared to the x, y and z variables when I'm dealing with problems of this kind. So now I have an electron around the nucleus at some r, theta and phi. And I would like to write my three-dimensional Schrodinger equation in terms of r, theta and phi instead of x, y and z. Correct? There's going to be a homework problem which lets you kind of interconvert between r, theta, phi and x, y and z. It's very simple to do that. You can just look at the geometry and you'll immediately recognize that I have these kind of transformations. My z is really r cosine theta. My x is r sine theta cosine phi. My y is r sine theta sine phi. Likewise, I can go back from r theta phi to x, y, z and vice versa. So these are my spherical coordinates. Now how do I write the time independent Schrodinger equation in terms of these coordinates? So the choice of coordinates is just for my convenience. So first of all, I will recognize that my wave function psi can now be written in terms of r, theta and phi. So this becomes a function of r, theta and phi. By the way, today is going to be an involved lecture, so you have to follow each and every step. So first of all, I can replace the psi x, y, z with a kind of r, theta, phi. My potential energy can be written in terms of x, y and z, r, theta, phi. So my v becomes now a function of r, theta and phi. By the way, if this were a positive charge here, a nucleus which is positive, let's call it the charge E on a proton, what would be the potential energy that the electron at point P sees? So what's the force, what's Coulomb's law? It just comes from the Coulomb's law. So this potential energy is simply the charge on a proton, the charge on electron, which is also E. You multiply the two together, E square over 4 pi epsilon naught. R square gives you the force and R gives you the energy. So I have E square 4 pi epsilon naught R with a minus sign because we have a positive and a negative charge. Okay, got it? Is this clear? The force is from the Coulomb's law is 1 over r square, and the force is really the integral of the energy. So you differentiate the force, you will get the energy. So this is the potential energy, and it depends upon r, and fortuitously, which means luckily, it doesn't depend upon theta and phi. So it's really a function just of r. It is independent of theta and phi. So what does this physically tell us? What does this mean? This independence of theta, independence on theta and phi signifies something. Right, so it's spherically uniform. On a sphere, the potential energy doesn't change. No matter where the electron is on a fixed sphere, its potential energy is going to be the same, because this really is considered to be a point charge. Okay, so however, if the electron tries to get closer to the nucleus, what's happening to its potential energy? So this thing is decreasing, so all of this is becoming more and more negative. So it's a stable situation. The electron wants to be close to the nucleus because the nucleus, after all, is positively charged. So the electron wants to get closer and closer to the nucleus and lower its energy. Got it? But why doesn't the electron fall into the nucleus? If you really want this energy to be as negative as possible, which is lower energy, why doesn't the electron fall into the nucleus? नहीं, फिर भी every system, natural system, wants to lower its energy. Yes, it has to do with the kinetic energy. There has to be a minimum energy, but okay.
It's not a closed system.
What is meant by a closed system?
Okay, it's not in isolation, right?
No, it's just consider this in isolation. Remember, when you don't have an answer to anything, what do you think about?
It has enough velocity to execute circular motion. It just revolves around.
All right, so uncertainty principle. So really, you cannot squish the atom. This electron cannot fall into the nucleus because if you confine it to smaller regions, its energy goes up. And if its energy goes up, the energy goes much larger than the ionization energy. So the electron just kind of flies out from the atom. You cannot squeeze atoms because of the uncertainty principle. If this R becomes infinity, what is the energy? 0, which is that the atom has ionized. All right. Now, quantum physics tells us that the total energy of the system is quantized. So far, this is just the potential energy part. So you take this potential energy part and insert it here. Now we need to care about this thing. Now really, what is the case is that all of this is an operator. Right? It's an operator. It's a second order derivative on the wave function. So it's called an operator. It's like a predator preying upon something. This operator is called the Laplacian. Laplacian. All right, this is a fancy name. And this Laplacian is also given a symbol. That symbol is this sign, which is called nabla. It's a vector and then you square it, right? So this is the symbol for all of this. Now what we've done is, here we have a one-dimensional system. Here we have a three-dimensional system. But we've expressed our Laplacian in x, y, and z coordinates. All right. We can also express our Laplacian in the polar coordinates, in the spherical coordinates. So in the spherical coordinates, this Laplacian is written in the following fashion, and you learn about this in your calculus 2 course. I cannot derive it in modern physics. So this Laplacian operator in spherical coordinates looks like this: 1 over r square plus sine theta theta. All right. So this is what the Laplacian looks like, and you don't need to remember this, but this is what it is. So now I can write my entire Schrodinger equation with this definition in the form minus h bar square 2m r theta phi minus Vr. I'm still going to write this as Vr. Vr really is equal to this function over here plus Vr psi r theta phi. This equals E psi r theta phi. All right. Now I need to solve this to find out the wave functions. All right. How do I solve this? I'll only solve it partially because the solution is very complex. It's not out of this world, but it's just tedious. And I'll give you a glimpse of what the solution looks like. Anyway, I want to solve the Schrodinger equation for the hydrogen atom, and my result would be wave functions. Those wave functions will have an r part, a theta part, and a phi part, just like the infinite well, but now a different kind of potential. The potential defines the wave functions. Everything else is just the same. It's the potential energy that is changing from problem to problem. Got it? So now, have you ever come across this ubiquitous word in chemistry? Orbital. So what is your conception of an orbital? What is an orbital? 1s, 2s, 2p, 3px, 3d squared. What is an orbital? A region, but electron could be found anywhere.
Highest probability.
Highest probability, okay. The wave functions are the orbitals. The wave functions that pop out from a solution of the Schrodinger equation, chemists call these wave functions orbitals. So the wave functions are just the orbitals. Now let's try to see how this solution over r square plus sine theta theta. All right. So this is what the Laplacian looks like, and you don't need to remember this, but this is what it is. So now I can write my entire Schrodinger equation with this definition in the form minus h bar square 2m r theta phi minus Vr. I'm still going to write this as Vr. Vr really is equal to this function over here plus Vr psi r theta phi. This equals E psi r theta phi. All right. Now I need to solve this to find out the wave functions. All right. How do I solve this? I'll only solve it partially because the solution is very complex. It's not out of this world, but it's just tedious. And I'll give you a glimpse of what the solution looks like. Anyway, I want to solve the Schrodinger equation for the hydrogen atom, and my result would be wave functions. Those wave functions will have an r part, a theta part, and a phi part, just like the infinite well, but now a different kind of potential. The potential defines the wave functions. Everything else is just the same. It's the potential energy that is changing from problem to problem. Got it? So now, have you ever come across this ubiquitous word in chemistry? Orbital. So what is your conception of an orbital? What is an orbital? 1s, 2s, 2p, 3px, 3d squared. What is an orbital?
A region in which an electron can be found.
A region, but electron could be found anywhere.
Highest probability.
Highest probability, okay. The wave functions are the orbitals. The wave functions that pop out from a solution of the Schrodinger equation, chemists call these wave functions orbitals. So the wave functions are just the orbitals. Now let's try to see how this solution comes about. First of all, I have a problem of this kind. It's a partial differential equation, and it has this r dependence, theta dependence, phi dependence. So what's the first thing my little heart would desire? What would I do at the first instance? Separation of variables. I take the wave function and I imagine that this wave function is really a product of three parts. So I take my wave function and I propose that this has an r part, depending only on r. It has a theta part, so this big theta, depending only on the angle theta, and a big phi that only depends upon the angle phi. So it's a product of a radial part, a polar part, and an azimuthal part. Radial, polar, azimuthal. That's the terminology I'm going to use. So the big letters represent the functions. So the wave function has been broken down into three wave functions. And I don't know if it's a solution. I just put this ansatz into this equation and see if I can get anywhere, somewhere. Alright, so let's try doing this, at least partially. What I can promise is that on the blackboard, I can derive this part for you. I can show how this part is derived. I have a PDF file typed up. I can show what the solution looks like, and this you can do on your own in any quantum mechanics textbook. Okay? Because otherwise I'll be spending the entire another full lecture on this derivation, a full lecture on this derivation. So let's put this ansatz into our wave function. So minus h bar square over 2m. What is m? Mass of the electron. All right. So 1 over r square, partial derivative r square, capital R. Right. So if I were to insert kind of this thing onto the left hand side, I just need to take the partial derivative with respect to capital R, because theta and phi do not depend upon R, and these factors will just appear as they are. Correct? That's the first term in the Laplacian. Got it? Because the partial derivative is only differentiating with respect to R, capital R. Theta and phi are constants as far as the first term in the Laplacian is concerned. Got it? So those functions just appear as they are. So now I'm not putting the arg. Now let's multiply both sides of this equation by r square sine square theta. The one thing I could do is I could take energy to the left hand side of this equation, make this equal to 0. So what I do now is I multiply both sides of this equation by this term, r square sine square theta. So I'm left with minus h bar square 2m r square sine square theta, sine square theta r plus sine theta plus plus r square sine square theta dr minus e equals 0. Got it? Now why have I, yes please, मल्टीप्लाई कर दिया r square sin square theta से. Got it? Now why have I done this? You don't know? Just look at this term over here. This term doesn't have any r in it. It doesn't have any theta in it. Right? It only has phi dependence. So I could take this to the other side of the equation. Right? Let me take this to the right hand side. Since I have the luxury of this erasure here, so I just kind of move this out from the left hand side and bring it here. Now I have a left hand side and a right hand side. The right hand side only has phi dependence and the left hand side is devoid of phi dependence. Devoid means it doesn't have any phi dependence. What does this mean? So you have an equation, a left hand side, right, and they're equal. One has a phi dependent part and the other doesn't depend upon phi. What does it mean? What does it mean? Sorry? There's no, come on, energy is just one small factor here. So they are equal. You have something that if phi changes, then this part must change. Right? If capital phi has a phi dependence, this part changes. But there's no phi dependence on the left hand side. So the left hand side cannot change no matter how much you change phi. Which means that this right hand side must be a constant. It must not even depend upon phi. Right? So if this is the case, we've seen this by the way in our infinite well and other examples. If this were the case, this right hand side must be a constant. And that constant must be equal to the left hand side as well. So minus 1 over phi d square capital Phi d phi square is some constant. Let's call it C1.
वैसे इसमें वो फैक्टर होगा ना माइनस एच बार स्क्वायर
हाँ यार, ओहो, excuse me. I want to get rid of this thing. so what I do is I multiply with 2m over h bar square. So I get a 2m over h bar square here. So I just gonna or negative sign. All right, is that okay now? So is this making sense? So now this is my one equation that I have. How can I solve this? What's the solution to this equation? So this minus sign kind of, okay, let me see if I'm doing the signs correct. So I keep this minus sign here. So when I take it to the other side, this becomes plus. Does this become plus here? Yes, I think yes. So this is like this. Anyway, it doesn't make much of a difference. So how do I solve this? What's the solution to this equation? I give you 2 or 3 minutes to work out the solution to this equation. Make an auxiliary equation. Solution, please. Excuse me, is a class going on? Anyone would like to show me a solution? This capital Phi is a function of small phi. If I were to write the auxiliary equation for this, this would be q square minus c1 equals 0. So the solution for this auxiliary equation is plus minus iota c1, right? Therefore, phi dependent upon phi is going to be proportional to some constant E a q square minus c q square equals I think there's a minus sign here. All right, there's a minus sign. So the solution will be plus iota under root C1 phi plus E minus I C1 phi. All right. All right. So now what I have is I have the azimuthal part of the wave function. Got it? All right. So there's something special about this C1. If, for the sake of argument, let me ignore this part for the time being. Let me ignore this part. And I will kind of show you that why ignoring this makes sense. If I have this wave function, which is the azimuthal part of the wave function, is this a periodic function? Which means if I took my electron, which were at this location at some value of phi, and if I turn it around by an angle of 2 pi, is the wave function going to change? The wave function should not change. So if now this is a spherical problem. If I had an electron and it's at some position, if I make it go around a circle on the equatorial plane or the azimuthal plane and I rotate it thoroughly by an angle of 2 pi, the wave function that I get after this rotation of 2 pi is going to be identical to the original, which means that this function phi is periodic. That means that if I were to take phi and I rotate this by 2 pi, I will get the original function. This is like a boundary condition. Now if I were to do that, if I just take this function, this part of the function, phi plus 2 pi, what do I get? E plus I C1 phi plus 2 pi. This is E plus I C1 phi E plus I C1 2 pi. Right? But this must be equal to this thing, which means that this must equal E plus I C1 under root phi. What does this imply? This implies that this term over here must be equal to 1. What does this imply for this exponent over here? 0 or a multiple of 2 pi. Any multiple of 2 pi works. And so therefore this exponent over here, C1 2 pi, is some multiple. Now I'm going to use a variable m, which is not to be confused with the mass of the electron. So let me put this variable with a small l for reasons that will become apparent later. So this is an integer ml. So any integer multiple of 2 pi works, right? So ml is some integer, which means that my under root C1 is an integer, or C1 is ml squared. C1 is the square of an integer. The integer could be 0, it could be 1, 2, 3, 4, minus 1, minus 2, minus 3. And since it could be minus as a negative integer, therefore this negative case subsumes this case, which means it works also for this term. So I'm justified in kind of ignoring this term in the calculation, because if it works for positive mLs, it works with negative mLs over here. It works both for positive and negative. So I'm kind of justified in saying that for this calculation I don't need to use this. I can use this if I would like, but the calculation becomes a bit lengthier. So the upshot is that the azimuthal part of the wave function is the following. The azimuthal part of the wave function is kind of some constant, right? I don't care about constants. Is E plus I square root of C1, which is this number ml phi. And this ml is an integer. It could be 0, plus 1, minus 1, plus 2, and so on. So now what I've done is I have solved the azimuthal part of the wave function. Now when I solve this, this thing equals minus C1. Minus C1 is minus ml square. So I can put minus ml square here and then see what my equation is going to look like. So what I do now is minus sine theta over r square minus sine theta over capital theta sine theta big theta small theta plus 2m over h bar square r square sine square theta v r minus e equals minus ml square. Now I have this equation in front of me. Got it? So I have solved at least the azimuthal part, and I've done a clear calculation in front of you on the blackboard. So now if I were to take my wave function, I know what my azimuthal part, what my phi part looks like. So the right hand side was a constant, that was C1. C1 is minus ml squared. ml is an integer. It comes out because the wave function has to be periodic. You cannot have a wave function that changes at this location every time you make a traversal. Okay? Therefore, now what we could do, if I take this equation and I divide both sides of this equation by sine theta. So when I divide by sine theta, this goes away. This goes away. By the way, I cannot kind of cancel out this because this is being acted upon by a derivative. One of the signs goes away over here, and I'm left with minus ml square sine theta.
In the start, isn't it sine square theta?
Sine square theta. So I divide by sine square theta. I'm left with the sine theta. Okay, you're correct. So I'm left with sine theta, and this just goes away. Okay, thank you very much. Now this is my new equation. I divide both sides by sine square theta. Yes, please. ML is this, is an integer. This comes out from the azimuthal part of the wave function. Yes, please. This term must be 1, which means that this thing must be some multiple of 2 pi, because ei 2 pi is 1, ei 4 pi is 1, ei 6 pi is 1. So therefore this term must be some multiple of 2 pi. Now that multiple is a factor, I call it ml. Alright? That's where it's coming from. Yes, please.
ML be positive because we initially
ML can be positive or negative, because this could be minus 2 pi, minus 3 pi, minus 6 pi, minus 8 pi, and so on. Right? So now this is our equation. Yes, please.
So why are we ignoring the negative sign?
This one. So now in the next step, ignore this part. Ignore this part and do this entire calculation. Since my ML can be positive or negative, it doesn't make any difference. Okay? Now this is my Schrodinger equation. What should be my next step? I have a part that only depends upon R, a part that only depends upon theta, a part that only depends upon R, and a part that only depends upon theta. So separate out, shuffle the two terms and bring the R dependent part to one side and the theta dependent part to the other side. So if I were to do that, I could just, let me write down this final form, minus 1 over R square plus 2m R square over h bar square. By the way, okay, fine. Vr minus E. This equals, I take this to the right hand side, 1 over sine theta, capital theta, all right. This is my Schrodinger equation at this point in time. I have a left hand side totally dependent upon R, exclusively dependent upon R, and a right hand side exclusively dependent upon theta, and the two parts are equal, which means both of the two sides must be equal to a constant, to the same constant. Let's call that constant C2. Now I can solve, I can bring this equal to C2 and solve it. I can bring this part equal to C2 and solve it. But the problem is that this is not a nice looking equation. I have not yet encountered equations of this kind. Therefore, I have to do some classic techniques pioneered by the greatest mathematicians of different times 2 centuries ago. This kind of equation was solved in the pre-quantum times by a French mathematician, Legendre, and this was also solved by, I think, another French mathematician, Laurier. So let me give you a glimpse of what the solution to this part looks like. Just a glimpse, and then we'll take a break. Any questions in the meantime? All right. I'll also upload this PDF. So I'm going to kind of walk you through in 2 or 3 minutes. Not going to show you the details of how one can solve at least the polar part. This is the polar part of the Schrodinger equation. So this is, I separate the variables. This is my definition of the Laplacian Schrodinger equation, all of this. So if I make any errors on the blackboard, you can actually follow this part on your own. Minus ml squared. We've seen this. Right. So now I have a theta dependent part and an r dependent part. The theta dependent part I call the constant C2, but this person, which is also me, calls it this constant L into L plus 1. Alright, I can do that, no worries. Any constant can be written as L into L plus 1. So I just take this equation number 3, which is the equation on the bottom right of the blackboard, and then I want to solve it. So this is my equation. This is, by the way, this is what I've done on the blackboard for you. So I don't want to go over this again. I've already done this. Now let's look at the polar part. This is my polar equation. I multiply this by capital theta, the function, and I write it in this form. Then I multiply by sine square theta. I write it in this form. Then I perform a substitution. I call cosine theta z, a new variable I introduce. Then sine square theta is this, dz by dt is this. All right. Now, how do I find? So this equation has d capital theta over d theta. So I want to express everything in terms of z. So I use the chain rule. I define theta to be equal to p. So theta function of small theta, I redefine it as a function of z. That function is p. So I just do substitution to the chain rule. You've learned all of this. It's just long. It just is a tax on your patience. Nothing else. No Facebook, no Instagram, Twitter is blocked anyway. Just your patience. 1 hour of patience. That's it. No new maths here. Then you kind of dp over dz. Then you take the double derivative, express everything in terms of p and z. All the thetas expressed in terms of z's. Everything. So now instead of an equation which has thetas and small thetas, I have p and z. This is the same equation written in different variables. And then I divide by 1 minus z square. This equation is a historically famous equation. It's a differential equation and it's called the Legendre equation. And it has set solutions. It has a set technique to be solved. Legendre, by the way, is pre-20th century. I don't remember if it was the 19th or the 18th century, but sometimes. And I think he used these equations to solve problems in fluid mechanics. Fluid mechanics, up till now, is the most advanced mathematical kind of physics that one can do. Alright, which is also useful. Of course, string theory might be more complex, but it's not useful. Anyway, so this is the Legendre equation. Now there are set solutions for this. One is a technique which is called a technique involving polynomials. So I express my PZ as a polynomial. GZ is some polynomial of z. A0 plus A1z plus A2z square plus A3z square. This is a power series solution method for finding the solution to a differential equation. So I kind of assume that I have a polynomial solution. I keep on multiplying things, I keep on differentiating things. This is the kind of monster that I get. All of it. And then I do another division. Come on. Here it is. Let me kind of. Alright, let me. All of this. All clean. By the way, nothing of this is something you can't do. It was detected, yeah. All of this. Now I have this equation. My G is now a polynomial in Z, a power series in Z. So the first derivative can also be found. I substitute these polynomial expressions into my big equation. This is what I get at the end. All of this. Now this is a kind of recursive equation. At the end, this is my final solution, part of it. This is what the coefficients in that solution look like. And it's a recursive. So you get 1, A0, you can find A1. Have A1, you can find A2, and so on. So it's a recursive solution. Finally, I have some constraints, and overall, this is my solution. I have also summarized the results for you. Is P, where P is given by this, where G is given by this, and my coefficients in the polynomial expansion are given by this, and there are certain constraints. The constraint is that my L must be equal to a maximum n plus the modulus of my constant ML. And all of this I then exemplify. When L equals 0, my ML must be 0 because of equation number 10, and then I can find my GZ, I can find my P's, I can find my theta, which turns out to be independent of theta. When my L equals 1, this is what my theta looks like. My L is mine, so and so on and so forth. So these are all the solutions for the polar part. Now let's take a 5-minute break, or a 5 to 10 minute break, and let's reconvene. All right, so quick recap. Now we have the hydrogen atom. Now please listen very attentively. An electron, just one electron, a lone electron, being a lone new proton. It's inside the field of a lone proton. Come on, Beto. And it's a spherically symmetric problem. That makes our life easy. So what happens so far is that due to spherical symmetry, we were able to separate out the wave functions. First of all, we found the phi dependent part of the wave function. I've shown you a glimpse of what the theta dependent part looks like, and you can look on your own what the r dependent part looks like. All in all, the wave function psi r theta phi has been broken down into 3 parts. An r part called the radial. This is a function of r. A theta part which is a function of theta. A phi part which is a function of small phi. And in the process, 3 kinds of constants or numbers have popped up. In an infinite well, we had a new number coming up which was small n. That was a quantum number. It identified that the energy was quantized, and wave functions were identified according to that quantum number n. In 3D, we saw 3 quantum numbers pop out, an x, n y, and n z. This is also a 3-dimensional problem. So 3 quantum numbers have popped up. One of them you've seen is this ml. A new integer has kind of come to the fore. A new integer has risen out of the ashes. ml. This is called a quantum number. ml is a quantum number and it can take integer values. 3 quantum numbers in fact in this 3-dimensional system appear. One is ml, one is called ml, another is called L, and the third one is called N. We've seen ml because we've explicitly done a derivation. When you solve for the radial part, this L pops out, and L and ml cannot be arbitrary. There is some relationship between ml and L, and the relationship is the following. N could be any integer or any whole number from 1, 2, 3 all the way up to infinity perhaps. L is also an integer that starts from 0 and goes up to n minus 1. The third is ml. So L depends upon n. The values L can take depend upon n. The values ml can take depend upon L. ml for a given L could be 0, 1, 2 up to L, but since ml can be negative, this could be minus 1, minus 2 up to minus L. And these wave functions are now dependent upon these quantum numbers. Here, this wave function over here depends upon this value m. So I can identify, I can put an ml to identify which wave function I'm talking about. Alright? Just as we had for an infinite well, the wave functions were characterized by n. But for an infinite well, we already had, for an infinite well in 1D, psi n x. Where does this number come from, n? This is really c of sine of n pi x over L. N is an integer starting from 1 all the way up to infinity. This is for an infinite well. So this wave function is now characterized by this number n. Likewise, this wave function r will depend upon n. Phi depends upon ml. Theta depends upon both L and ml. In fact, this thing, which is the angular part, this is the radial part, and the product of these is the angular part. Does the angular part depend upon the potential energy? No, because so far the potential energy Er is not being used anywhere. The only thing that is helping us is that it's spherically symmetric, but the potential energy does not identify these wave functions. They do not determine these wave functions. So the product of theta and phi, the product of theta and phi depends upon ml, theta depends upon both L and ml. And the solution that I've shown on the notebook kind of corroborates that. The product of theta and phi is a famous function in physics. Famous function in physics, which is represented by capital Y, which is a function of theta and phi, and it's parameterized by these two quantum numbers L and ML. So theta and phi, the product is generally written as capital Y, function of both theta and phi, and it is characterized by L and ML. These quantum numbers L, ML and N are also sometimes given special names. This is sometimes called the orbital quantum number. ML is called the azimuthal or magnetic quantum number, because this is like this gives rise to a magnetic moment. N is called the principal quantum number. So the product of theta and phi is represented by capital Y. All right, and this Y is a special function in physics. It's called, does anyone know what it's called? Spherical harmonic function. And this R depends upon N. So the solution for, let me use, because I might need to use the projector, so let me use this. So overall, the solution of the Schrodinger equation for a hydrogen atom in a spherically symmetric potential is R, which depends upon N, function of R multiplied by a spherical harmonic function Y, L, M, L, theta, phi. Three quantum numbers N, L and ML. The quantum numbers are mutually constrained and they quantize certain things. I'll show later. Now I've given you a piece of paper, and on this piece of paper there's table 13.1. I have a list of spherical harmonic functions for different values of N, different L and ML. The superscript is the value of L. The superscript is the value of L. The subscript is the value of ML. Acha ulta hai. Khair, alright. So let me conform to what I've given to you, right? So there are different conventions. So in this table that I've provided, this is L and this is ML, sorry, just convention. Alright? And in table 13.2, this R depends upon both N and L. Alright? R depends upon N and L. So these are two tables that are provided to you. For example, first of all, we decide what these wave functions are called orbitals. Now let's first of all make a table. N, the minimum value of N is 1. When N is 1, my L can be only 0. When L is 0, my ML can also be 0. That's it. So for this trio of quantum numbers, my wave function is going to be R, N, L, 1, 0, function of R multiplied by spherical harmonic. L is 0, 0, theta, phi. So I take up the entries from these tables and I can write this as 2 times 1 over A naught cube E minus R over A naught, and this is just a constant. All right, so this is 1 over pi a naught cube e minus r over a naught. This is my wave function for n is equal to 1, L equals 0, ml equals 0. This is the overall wave function, my psi. It turns out to be a real wave function.
Sir, is psi not better?
It depends on r, theta and phi, but in this particular case it doesn't depend upon theta and phi. All right? Got it?
Psi of r.
यार लिख लो यार. You can write r, theta, phi. So this is my wave function for n equals 1, L equals 0, ml equals 0. This is one solution to the Schrodinger equation. Now this wave function, what does it represent? First of all, luckily, I can draw this wave function. Does this wave function have any theta dependence or phi dependence? It doesn't. Whenever L equals 0, ml can only be 0, no matter what the value of n is. And such wave functions do not carry any theta or phi dependence. They are this, if you're at a constant, they only depend upon the radius. How far is the electron from the nucleus? So no matter where you are on a sphere, the wave function remains the same. It doesn't depend upon theta or phi. Chemists call such an orbital an s orbital. Since n equals 1, this is what chemists would call a 1s orbital. All right. Now, if I keep on building this table, let me kind of look at another term. N equals 2. For n equals 2, my L could be 0 or 1. So let's first look at 0. When L equals 0, ml must be 0. So for this, my wave function, which I now write as n L ml, I can write it in this fashion as well. Theta phi r for n equals 2, L equals 0, ml equals 0. I take my r part from this table. I take r2 0 part. It's 1 over 2 1 over 2 a naught cube minus r over a naught plus 2 e minus r over 2 a naught multiplied by 3 over 4 pi, come on, cos theta, इधर घुस गए हैं. All right, but by the way, what is a naught? A naught is the Bohr radius. It's a function of epsilon, m and h. So I can even write down the value of a naught. Oh, sorry, 1 over 4 pi. Sorry. It's 1 over 4 pi. 1 over 4 pi. It's another s orbital. A naught is. Does anyone remember a naught? half an angstrom, 4 pi epsilon naught h bar square m e square. It's about half an angstrom, whatever the value is. You learned this from your old Bohr's quantum model. So this is the wave function for n equals 2, L equals 0, ML equals 0. Does this have any theta or phi dependence? Excuse me, anyone who hasn't spoken so far. Does this function have any theta or phi dependence? Come on. Does it depend upon theta or phi? No, it doesn't. Because L equals 0 and ML must be 0. So this is also an s orbital. This is called the 2s orbital. If n equals 2, L could be 1. When L equals 1, ML could take up 3 kinds of values. It could be 0, it could be plus 1, it could be minus 1. Alright. Now first of all, let's look at the 1s orbital. Let's look at the 1s orbital and let's try to plot it. Let's try to make a diagram of an orbital. Okay, let me use this part. 1s orbital. The wave function is for the 1s orbital. So this is shorthand 1s. 1s is 1 over pi a naught cube e minus r over a naught. Can I plot this? There is no theta and phi dependence. No theta and phi dependence. I can plot with respect to r. If I plot this wave function 1s, what would the plot look like? Exponential decay. So this is the plot of the wave function. So I can plot the wave function. So first thing I've done is I plotted the wave function. Chemists like to plot or draw orbitals. They are more adventurous sometimes than physicists. They like to draw orbitals. So how can I draw this orbital? If I were to draw an orbital which does not have any theta and phi dependence, the best kind of drawing I could make is a sphere. So when one would like to draw a 1s orbital, this is what generally is drawn. This is a 1s orbital. Generally you'd like, sometimes you would like to kind of put this in a cloud format, an electron cloud. But what does quantum physics tell us? Quantum physics tells us that wave functions on their own do not have any meaning. It's the modulus square of the wave function that is important. So if I plot, so this is a plot of 1s. So if I'm just focusing on 1s orbital. If I plot the modulus square of this wave function, what will that look like? Roughly the same. So if I take the square of this, I'll get 1 over pi a naught cube e minus 2r over a naught. I will just get roughly the same thing. Decay is faster because of this factor of 2. Now what does this represent? So according to your proposal, where is the highest probability of finding the electron? At the nucleus? This is r equals 0 at the nucleus. But this is kind of puzzling because we've seen that this is against the uncertainty principle. So this is really not the true probability density. Reason. Any reason? Because of this is not psi square. This psi square does not really represent kind of, this is not representative of the probability density for a good reason. I want to explain that in some detail. But before I explain that, I would also kind of like to look at something really interesting and graphically appealing. Let's look at this function. So I owe you an explanation. The explanation that I owe you is, why isn't this a probability density function? Because this doesn't look right. This thing is going to show us that the probability is maximum at the nucleus, but that's never the case. That's not the case. So I owe you an explanation to that. Probably in the next lecture I'll explain that because this deserves attention. However, what I would like to do at this juncture in time is, let me draw another orbital. Right now I'm only tasked with drawing the wave function and the orbital and the square of the wave function, but I don't know at this point in time what does it mean. Let's look at this thing here. Psi, n is 2, L is 1, ml is 0. What is the wave function? Let's look at our tables. R21 is 1/2 1 over 6 a naught cube r over a naught e minus r over 2 a naught. This is my r dependent part, so let's separate out. This is my r 2 0 and my y 0 by 1 0. L is 1. What is this equal to from my table? This equals the second entry, 3 over 4 pi cosine theta. Now I can plot this. Yes, please. My friend, you're asking a question? Yawning? Alright, so if I were to plot this, let me plot the r separately from this thing. If I were to plot the r 2 0, what is a plot of this object going to look like? So this is an exponential, but this is a rising r. So this is 0 at, this function is 0 at r equals 0. So this gives a rising part, this gives a decaying part. So you'll get something like this. So this is a plot of r. This is what the radial part of the this is a 2s orbital. This is what the radial part of the 2s orbital looks like. In fact, you'll find out that this peak is at 2 times a naught, 2 times the Bohr radius. We'll continue this discussion in the next lecture, by the way. So this is the radial part. How can I plot the angular part? I want to plot the angular part. Now this is a function of theta, so my at best what I could do is the following. Let's try to plot this thing. I plotted the radial part for the 2s orbital. This is the radial part for the 2s orbital. Now I'm going to plot the angular part for the 2s orbital. At least I'm going to make an effort. Let's try doing an effort. Yes, please. L to 0. L नीचे लिख रहे हैं. My what am I choosing? My L equals 1. Oh yeah, this is 2 1. Sorry. N is 1, L is 1. It's a 2p orbital. Correct. It's a 2p orbital. Sorry. It's a 2p orbital. Because L is 1. L is 1, ML equals 0. So this is the row that I am considering. It's not a 2s orbital. This is a 2s orbital. This is a 2s orbital. So how can I plot this thing? Any ideas? I want to plot 3 over 4 pi cosine theta. This is why, let me be clear, L equals 1, ML equals 0, theta phi. Let me draw 3 axes, x, y and z. I want to plot cosine theta. I want to plot a wave function that is proportional to cosine theta. So where does this have its maximum value? At what theta does this spherical harmonic have its maximum? At theta equals 0. At theta equals 0, this is equal to 1. At theta equals 90 degrees, this equals 0. What about theta equals 180 degrees? Minus 1. For theta between 0 and 90, this is positive. For theta between 90 and 180 degrees, this is negative. So now on this axis, if I'm above the xy plane, my theta is positive. Remember my sphere that I draw? Theta is the angle from the z axis. If I'm above the xy plane, my theta is between 0 and 90 degrees. My cosine theta is positive. Maximum value over here when my z is 0, and it drops to 0 when my theta is 90 degrees. When is my theta 90 degrees? On the xy plane. So I could try to draw this in this fashion, a pier like this. So this is what chemists like to draw, and in this region the wave function is kind of positive, and I'm able to draw this wave function in the first place because it's a real wave function. The wave functions can be complex. Look at some entries in the table. Sometimes you get complex wave functions. So in this region the wave function is positive. However, when I go below the xy plane, my theta becomes greater than 90 degrees and I'm approaching 180 degrees. And cosine of an angle greater than 90 and less than 180 is negative. But still I get a maximal negative value at 180 degrees and 0 in this plane. So as I move down towards the south pole, the wave function grows bigger and bigger in size like a cosine function. So I get a kind of a cosine dependence over here. However, the only difference is that this part represents a negative wave function. Now this is a p orbital because L equals 1, ml equals 0, that's why it's called a pz orbital. This is what chemists like to call a pz orbital. Pz orbital. And this does not depend upon r. Any pz orbital, whether it's 2pz, 3pz, 4pz, 5pz, transition metals, lanthanides, anything, the pz orbital will have an angular dependence that looks like this, which is then multiplied with something which is radially changing, and I'll show you how that looks like. So anyway, this is what the pz orbital looks like. Excuse me, you have to be patient. The time ends at 4:15. I'm going to end at 4. You have to be patient. All right. So now, if I were to look at this orbital, this is a plot of y, the spherical harmonic function, which is the chemist's orbital, pz orbital. If I take the modulus square of this, everything becomes positive. This is the general diagram for a pz orbital that you find in a textbook on chemistry or physical chemistry, right? Sometimes you would like to draw this as a cloud of electron, as a probability density cloud. Higher probability density near the z-axis, now px orbital. So I'm just going to finish. This is a pz orbital. If I were to consider a px orbital, which is L equals 1, ml equals 1, this is really not a px orbital. So if I would just look at the spherical harmonic associated with this, the spherical harmonic L equals 1, ml equals plus 1 is minus 3 over 8 pi sine theta e raised power plus iota phi. Now this is a complex wave function. I can't plot it. If I were to take L equals 1, ml equals minus 1, this would become plus 3 over 8 pi sine theta e minus I phi. I can't plot it. However, if I take the sum of these wave functions, I create a superposition of these wave functions. I can create superposition of wave. If this is a solution to the Schrodinger equation, this is a solution, then the sum of these will also be a solution to the Schrodinger equation, because it's a linear equation. So if I were to take the sum of these, 3 over 8 pi, the minus sign, I will get something of this kind, sine theta, something proportional to sine of phi, sine theta sine phi, right? I can plot this now, and if I were to plot this on my x, y, z axis, x, y, z, y sine phi because e I phi minus e minus I phi because these are different signs gives me a term proportional to sine phi. So now I have sine theta sine phi. If I would like to plot this superposition, this is maximal when theta equals 90 degrees. So I get maximal wave function in the xy plane, and I get maximal wave function when phi equals 90 degrees. So my lobes will now lie along the y axis, and I get 0 wave function on the z axis, because here theta is 0. This thing is maximum when theta is 90 degrees, so I'm on the xy plane, and phi is maximal. This thing is maximal when phi is 90 degrees, so I'm on the y axis when phi is 90 degrees. This orbital, chemists call this a p y orbital. Likewise, if I take the superposition which I subtract the two wave functions, I will get a p x orbital. By the way, this is also positive and this is negative, or vice versa. So this is how I can draw orbitals. So please try to do practice with a d orbital. Forget about the radial part. Practice with a dx square minus y square orbital, or a dxz orbital. It's very simple to draw these orbitals. So let's continue this discussion on Thursday.